Good morning, everyone. My name is Shushu. I am a senior engineer at Changeis working at the Volpe Center. Today, I am going to talk about some modeling approaches developed at the Volpe Center to investigate loading and failure of railroad track components. The background of this research originates from several recent derailments caused by broken spikes. Those broken spikes were found typically on the curved track with elastic fastening system. The breakage location of the spike was usually 0.5 to 2 inches below the surface of the timber tie. This slide shows the pictures taken after the derailment in Vandergrift, Pennsylvania. In this picture, the timber ties were severely damaged. You can also see the breakage location of the spike, 0.5 to 2 inches below the surface of the tie. However, why so many spikes were broken and what is the root causes for broken spikes were not very clear at that point. So, in this presentation, we are aiming to investigate the root causes for spike failure in elastic fastening systems used with timber ties. We'd like to understand the failure modes of the broken spikes, what level of forces required to initiate the failure in a spike at a component level, and also what is the force distribution mechanism to transfer the force into a spike at a system level. Once we have a better understanding on the derailment, we'd like to propose remediations to prevent this happening again. This slide shows the load path and the associated models we use for each path. For example, from rail to plate, there's a wheel load applied on the top of the rail, and the rail is very sensitive to temperature and generates thermal load, usually along the longitudinal, which is the track direction. The wheel and the thermal loads then distribute to the plate. We call it plate load. How the load is distributed to the plate load depends on two things. One is the fastener stiffness, and the other one is whether anchors exist or no. In our research, we use an analytical track model composed of vertical, lateral, and longitudinal spring series to estimate the plate load. Next, when the plate load is then distributed to each spike, we call it spike load. This load path is affected by plate tie friction and the spike engagement within a plate. To estimate the spike load required to initiate spike failure, we build a finite element model. This model is composed of a spike, a plate, and a timber tie. Taking different magnitude of spike load as an input, we are able to see the minimum force required to initiate the spike failure. This slide shows the typical failure modes from the single spike finite element model. We use plastic strain as an indicator to predict the location of spike failure. The contour shows where the spike failure would initiate under different loading scenarios. Depending on the loading condition, the spike can experience lateral, longitudinal, and mixed bending failure. For example, under a combination of lateral and longitudinal loading, the spike has a mixed bending mode and the failure happens at the edge of the spike shaft. Here is a spike that was about to break, found at the horseshoe curve. Comparing the actual spike with the combined bending failure mode, the failure mode and the breakage location is very close to each other. The figure on the right showing the wood damage by the end of the loading. The most severe damage of the tie is around the spike area on the top of the tie. One of the benefits using the single spike finite element model is that we're able to create a failure envelope that shows the minimum spike required to initiate wood tie damage and spike damage in either lateral, longitudinal, or both directions. What this figure tells us is that the curves are the threshold values that cause wood tie damage or spike damage. Any spike load inside the curve is considered as a safe load that is not going to cause any damage. Any load outside the curve is going to initiate either wood or spike failure. Because wood is an isotropic material, that means the longitudinal direction is much weaker than the lateral direction. So, the load required to damage the wood longitudinally, shown in the blue line, is smaller than the load required along the lateral loading direction. Because of the weakness of the wood in the longitudinal direction, the spike stress is affected in a very similar manner. If you look at the red curve, which shows the spike failure initiation, only 2,300 pounds of force along longitudinal direction is able to initiate the spike failure. But when you look at lateral only direction, you need 3,500 pounds of force in order to initiate the spike failure along the lateral direction. Once we know the fundamental force level to initiate spike failure, the next question is how we get that amount of force transferred here. So we have this track model that is able to help us understand the force distribution at a system level. This model is composed of vertical, lateral, and longitudinal springs. Based on beam elastic foundation theory, this model is able to tell us the plate load in all directions once we tell the model the train information and the stiffness of the springs. Next, I am going to use the horseshoe curve investigation as an example to illustrate what we have learned from our models. The horseshoe curve is located in Altoona, Pennsylvania. It has a very tight degree curve with steep grade. We investigated two tracks on this curve. Track 1, which is a downhill track without anchors. Fewer broken spikes were found at this track. And track 3, uphill track with anchors. Lots of broken spikes, especially on the high rail side, were found at this track. We pick one train from each track for the model demonstration purpose. These two trains have comparable axle weight and are running at very similar speed. Here is the instrumentation installed by University of Illinois. The strain gauges were installed at the rail to monitor rail forces in all directions. The LVDTs were installed to measure the displacement of plate related to rail and the displacement of a plate related to tie. All the displacements were measured in 3 directions. Here is an example of plate load distribution from the track model. 2 locomotives were used in this figure. The plate loads were plotted in vertical, longitudinal, and lateral directions. The lateral and vertical plate load distribution patterns were very similar. You can see 12 evident wheel loads. However, the longitudinal plate load distribution was quite different. The load influence zone was larger. The wheel loads were not seen very clearly in the curve. If you look at the vertical plate load distribution, which shown in black, there you will notice there are places with a positive vertical plate load. This indicates the plate was uplifting. This finding is very important because when you think of a force analysis diagram shown on the right side, there are plate loads in 3 directions, which is F vert, F flat, and F non. When those plate loads transfer to spike loads, we need to consider friction for the lateral direction. However, the longitudinal load is always preloaded on the spike when the vertical load is 0 due to uplifting effect. So the friction does not play a role along longitudinal direction. Once we convert the plate load to spike load, we plot the loads as a x-axis of lateral spike load and the y-axis of longitudinal spike load. You'll get a series of data points shown in this slide. We overlay these data points with the failure initiation curve we developed using our single spike FE model. We are able to evaluate the effective loading environment at the horseshoe curve. Here, we assume 100% of plate load goes into one spike, and the coefficient of friction between the plate and tie is 0.3. Again, compared with the spike initiation curve shown in red, all the data points inside the red curve are the loads that is not going to initiate spike failure. All the data points outside the red curve are the critical loads that causes spike failure initiation. On track 1, you can see a few lateral spike loads beyond the curve, and on track 3, there are some lateral spike loads and a combined lateral and longitudinal spike loads outside the curve. This slide evaluates the effect of spike engagement by assuming eta equal to 100%, 75%, 50%, and 25%, meaning the percentage of the plate load distributed to each single spike. Ideally, if there are 4 spikes within a plate, each spike would get even load distribution from the plate, which is 25%. However, this is not always the case from the field. From previous field investigation, one spike could take over 70% of the load while leaving the rest of the spikes are unloaded. This figure tells us two things. Number one, as the percentage of the payload distributed to one spike decreases, more spike loads shift inside the spike failure initiation curve, which indicates they're safe. Number two, when one of the spikes fails or missing, the rest of the spikes would take more percentage of the load, which would shift the spike load outside the failure initiation curve and increase the risk of spike failure. This slide compares the effect of coefficient of friction between the plate and the tie. The coefficient of friction has no effect on the longitudinal spike load because of plate uplifting, which we talked about previously. So the friction does not play a role here. But the coefficient of friction does affect the lateral spike load. When the coefficient of friction increased from 0.3 to 0.7, the friction increased. The percentage of the plate load transferred to each spike decreased. So the majority of the lateral spike load was shifted inside the curve when the coefficient of friction is up to 0.7. Since the magnitude of longitudinal load does not change with the friction, we have to think of other ways to mitigate the longitudinal load to make sure all the longitudinal spike loads fall inside the failure envelope. One of the remediations we're looking into is the feasibility of using composite tie. Here we're talking about the glass fiber reinforced composite tie. Unlike timber tie, this tie is isotropic, so the lateral and longitudinal directions have the same material properties. This tie is composed of a 0.5 to 1 inch skin, and inside the skin is core. The skin provides a much higher modulus of elasticity, MOE, and the strength is higher than the core. Compared to the timber tie, the material properties of this composite tie are stronger in the longitudinal direction. This figure summarizes the literature review conducted by University of Illinois and shows the weakest composite compressive strength is 34% greater than the strongest timber perpendicular to the grain. Composite MOE is more comparable to timber perpendicular to the grain MOE. This data also show that the median composite compressive strength is 100% and 150% greater than the median of the timber perpendicular to the grain. With all these statistics, this study aims to identify how important these parameters play in a role in spike stress reduction for heavy axial load environments. We continue to use our single spike finite element model, but modified all the material properties of the tie to present the composite tie behavior. At the same time, a lab test was set up by University of Illinois. A single spike was installed in the composite tie and loaded in the longitudinal direction. Strain gauges were attached on the spike 1 inch and 2.25 inches below the tie surface. Those recordings were compared with the model as validation purpose. To investigate the effect of tie strength on the spike stress, tie compressive strength was varied from the minimum value to the median value, then to the maximum value found in the literature review, which is from 1,000 to 2,500, then to 6,600 psi respectively. The spike stress in the timber tie under the same load was also plotted for a comparison between the two materials. Some key findings were summarized on this slide. Generally, compressive strength of the tie plays a very important role in spike stress deduction under the longitudinal loading direction. A higher strength of the tie keeps the tie in a very good shape, so the less stress is distributed to a spike. When the tie is strong enough to take all the load, the compressive strength of the tie is not sensitive to spike stress deduction anymore. This slide shows the effect of MOE on spike stress. The results indicate an inverse relationship between tie MOE and the maximum spike stress. As the tie modulus is increased, the maximum spike stress decreased. This is a result of reduced spike bending due to greater confinement provided by the tie. Although an inverse relationship between elastic modulus of the tie and the spike stress was confirmed through our study, the reduction is very marginal, less than 2%. The following 2 slides summarize the findings through this study. Some key takeaways are because of the anisotropic material of the timber tie, the longitudinal force required to initiate spike failure is less than the lateral force. This results in different spike load distributions when it comes to different loading environment. At the horseshoe curve, broken spikes on the downhill track, track 1, likely results from significant lateral loading condition. However, on the track 3, which is the uphill track, the broken spikes likely result from a mixed loading conditions with the lateral and the longitudinal loads. The tie compressive strength plays a very important role in spike stress distribution. The glass fiber reinforced composite tie provides high compressive strength and effectively reduces spike stress under longitudinal loading direction. The last but not the least, these models can be used as a tool to assess the loading conditions in the field at a system level, so it can provide insights to advancing track safety. Moving forward, one of the future research studies we are considering doing is that to expand our current model capacities to include more loading conditions, such as thermal load, ankle force, and so on, because they are very important. We are also looking forward to more collaborations on the field tests on the composite tie to see the long-term performance in a heavy haul environment. And also, alternative remediation methods will be looked into for spike load mitigations. In the end, I'd like to thank the Track Safety Research Program of FRA, Office of Research, Development, and Technology. The support provided by FRA is greatly acknowledged. The field data provided by University of Illinois for model validation is appreciated as well. With that, I would like to conclude my presentation. If you have any questions, let us know, and we are happy to discuss. Thank you for your time.